Perfect. So thank you very much for the invitation. It's always a pleasure to be able to talk about my research. And I hope what I'm going to explain will be interesting for you, and feel free to stop me at any point and to ask any question. So this talk is about some recent work that I did, and so I will start with the motivation about this kind of research, about using sampling to improve learning, and I will explain a bit what I mean with that. I will explain the general approach, and then I will present 3 different applications. One for expression recognition, one for weakly supervised object detection, and one for Bayesian weakly supervised localization. And while the first application, it's work that has already published, the second and the third are ongoing work, so I won't present much about results, but I think it's still interesting to see. So motivation of this work is, it's well known that deep learning models are very expensive and large. So it's very difficult to train those models. We need the large machines with GPUs, and every year, they're getting more and more computationally expensive. So in the past few years, there have been a lot of research in trying to reduce the computational cost of those deep learning models. But most of the approaches, they reduce computational cost at inference. So it means they reduce computational cost once the model is already trained and for deployment, and which is very important because we want to use these models also on embedded machines, and so with low computation. But apart that, it hasn't been overlooked. It's working with reducing the computational cost during training. And we can see here some examples of reducing computational cost at inference. For instance, we have weight pruning, where we reduce the number of weight or connections in a neural network based on the strength of these connections, trying to maintain performance but reduce the computational cost. Then there are matrix decomposition, for instance, for convolutions. I won't enter too much in detail because this is just to tell you that there are many different approaches for reducing computational cost at inference once the model is already trained. For instance, also something very used is quantization, where instead of using floating point representation for weights and data, we use integers. There is computational conditional computation, where the computation is it's reduced based on the difficulty of the samples. There is distillation. There are also specialized architectures. But the point is, can we reduce the computational cost during training? And why this is important? It's important because, as I said, computational deep learning models are getting more and more expensive, and for training. For instance, for language model, the famous GPT-3 model from OpenAI, they estimated a cost of several millions to train it with Tesla V100 cloud instance. So you can see that it's trying to reduce this computational cost. It's important for the environment and for cost, for everything. Same also for instance, the neural network architectural search. There was a method a few years ago that was using reinforcement learning, and in the paper, they said that it took 3-4 weeks to train that model with 800 GPUs. So you can see that it's a crazy amount of computation. Of course, there are also methods that are cheaper, but in general, trying to reduce the computational cost of these approaches, it's an important task. So how to reduce computation cost during training? One way would be to reduce the number of epochs in training, but normally this it's not very effective because you end up with a solution with a model that loses also performance. Another approach is to reduce the computational cost is to reduce the computational cost of inference, because during training we need to perform a forward propagation, which is exactly inference. And then if we reduce the cost of inference, then we can reduce computational cost of training. But most of the methods that I presented before, they cannot be used for reducing computational cost during training. For instance, quantization, it's difficult to use quantization during training because with quantized weights, we cannot use backpropagation. For pruning, again, the same thing. We can prune a model once it's trained. Pruning a model during training, it's difficult and doesn't work very well. Same distillation and same for many other approaches. So the bottom line is that most of the methods for reducing computational cost, they need a trained model. So in this talk, we try to see other approaches to reduce the computational cost of training. And if we think about training, we can think about training as a loop where at each epoch, we want to fit a model to the data. And for this, we have a loss and we try to, we compute gradients. But in general, at very high level, we want to fit a model to the data. And we will stop this at convergence. An interesting way to exploit this fact that we see the same data multiple times is to try to approximate some variables, some data that is used during training with some unbiased estimation. For instance, we can use Monte Carlo sampling to approximate some variables using during training. For instance, we can approximate a mean of n elements with k samples. So instead of computing the entire mean with n elements that will have a computational cost of n, we sample in a uniform way only k elements. So we have to evaluate k elements instead of n. And if this k is much smaller than n, we can save computation. How can we use Monte Carlo during sampling during learning? So we said that we have to fit a model on the data multiple times. And we can imagine that in this model, we have some functions that can be either computing a mean or a sum. For instance, if we compute convolutions, we are computing multiple sums of the scalar product between the filter and the data. And so we can approximate some of this with Monte Carlo sampling. Again, the same formulation as before. Instead of computing the entire mean or sum, we compute only one part of this. And the good point is that this estimation is unbiased. So it means that if we have enough samples, we end up with exactly the same estimation of the mean. And so it means also that in expectation, we are still optimizing the same loss as if we compute the exact model. So finally, we can see that this is a trade-off between reducing the computational cost because we sample some of the data instead of computing all of it, and an increased variance because when we sample part of the data, of course, we will have more variance in the estimation. But the interesting point is that in some cases also the variance can be beneficial. It's a kind of regularization. If you think about dropout, for instance, it does exactly that. It drops some neurons and it increases the variance, but it's helpful for a better learning. An example of this kind of approach of using Monte Carlo sampling for reducing a computational cost is stochastic gradient descent. If you think about stochastic gradient descent, what they do is instead of computing the entire loss on all n samples, we select a subsample of these n samples. We select again k samples, what we call normally a mini batch, and we compute the loss only on this mini batch, which means that we have an estimation of the loss with some increased variance, but we can reduce the amount of memory needed because we don't need to compute the loss on the entire training data, but just on a subset. And we can still use parallelization within the batch. And finally, stochastic gradient descent, we can say that it's used in most of the deep learning models. And without that, it will be very difficult to train a model. So we can see that Monte Carlo sampling has already quite some important usage for training. But here in this talk, we try to go farther to use this kind of approach in other ways. So exactly the question is, can we use Monte Carlo sampling for other training variables? So for using the same kind of sampling approach to reduce the computational cost of some other parts of the training? And the answer is yes, because for instance, we could use this approach for pooling in convolutional neural networks. Because I talk always about convolutional neural networks because of course my background, it's mostly computer vision. So we use a lot of convolutional neural networks, but the same thing can be also for like recurrent neural networks or for transformers models. Finally, in most of these models, we need to compute means or sum, and there we could use a Monte Carlo sampling approach. But the problem is that if we use the standard approach where we sample in a uniform way, finally, we are still playing with this trade-off between an increased variance and a reduced computation. And that can help a bit, but at the same time, we're playing with the same trade-off as the stochastic gradient descent. So what would happen in many cases is that we reduce the computational cost with by estimating some variables in the training, but this reduction of computational cost will produce an increase of variance. So the increase of variance will require, if it's too much, will require a larger batch size. So the gain that we got with the sampling of some variables will be lost because we will need a larger batch size to reduce the variance again. So what else we can do? We can try to approximate something different than sums and means with Monte Carlo sampling. For instance, we can try to approximate max. In many deep learning models, we need to compute the max of some variables. For instance, a very commonly used kind of pooling is max pooling, where we pool the maximum value within a certain region of interest. And also for object localization, if you think about it, we have many possible locations where an object can be, and we select the location that scores the highest. So again, we compute a max to localize the object. The advantage of trying to approximate a max compared with the mean is that if you think about the max, it's trying to localize the highest value within a certain range of values. So if we sample and we are able to sample and find the max at the end of the training, we will sample always the right location. So this means that the induced variance will be very low. So it means that we get the advantage of reducing the computational cost, but we won't introduce additional variance. So it's a much clean gain than what we saw before. The disadvantage of this is that for computing something for sampling in a non-uniform way, we need to keep track of where to sample. So this will introduce some additional memory. So that's a bit the trade-off. We will build a model that will require a bit more memory for keeping track of where to sample, but it will reduce computational cost and it will reduce by a large margin, normally also the general memory needed. Okay, this was the main overview of what we do. And now I will start to introduce a specific application of this approach. I don't know if there are any questions before going to the applications. If there isn't any question, I will go on. So first application, emotion recognition in videos. I did this with some students and colleagues. So here there are two students, Theo Arial and Massi, which were master students with myself and my colleague Eric Granger. And also this work was done with also Patrick Cardinal, a prof on the Department of Log TI in ETS, and also with the collaboration of Simon Bacon, which is prof at Concordia and part of Lattice. And with him and Eric, we have also some very interesting projects about not only recognizing emotions, but also more difficult expressions like ambivalence or other kind of subtle expressions. But here I will present our previous work on emotion recognition. So the idea is that we have a video. For instance, here on the top, I saw some frames of a video. So this guy is not a collaborator of this research. It's just a video where we try to extract emotions. And you can see in this video, maybe I will go already here. You can see in this video that emotions are changing over time, over different frames, and often not on the entire sequence we see an emotion. For instance, in this case, the emotion is mostly at the end of the video where the guy is kind of smiling. So the emotion of this sequence would be probably happiness. But we notice for getting good results, we cannot consider all the frame with the same importance. So what we did as a first step was to introduce temporal pooling that is trying to summarize the information of the entire video, but in a smart way. And for each frame of the video, we use standard 2D CNN that will tell us which is the emotion that is more likely to be extracted. So as I said, we want to find the most interesting part of the video with a temporal pooling. And what we introduce, it's what we call softmax for temporal pooling. So instead of using assigning the same importance to every frame of the video, and instead of also using some more complex attention that will require extra parameters. Here we use the softmax attention. And what is, it's something very simple. Imagine that we have a function f that is our convolutional neural network that given a frame of the input that we call xt will give as output the probability of a certain action. And what we'll do to compute the probability of the entire video x, it's to sum the probability of each frame, but weighted by a weight wt associated to each frame. And what is this weight? This weight is a softmax on the probabilities of the given action or the given emotion, sorry. We compute with this probability as softmax, and this softmax is tuned by a factor t, capital T, which can be thought as a temperature, so that if this temperature is high towards infinite, we go back to average pooling so that we give the same importance to each frame. And if this temperature is close to zero, we go to max pooling, where we select a single frame, the maximum scoring frame, as representative of the entire video sequence. So with this approach, the advantage is that we have this parameter t that we can tune, and based on the data on a validation set normally, we can decide if for a certain kind of video or data, it's more important to try to look everywhere in the video or to focus on a very specific part of the video. And this work was a paper that we published in 2019 in a local conference here in Canada, and it was well received, and we ended up getting the best paper award for this work, so we were quite happy. And here you can see an example of what we do. We have our video again, and we can see at the bottom the value of W, the importance, the weight that we associate to each video. And you can see that, as expected, we give more importance to the part where the person is expressing the emotion. Finally, I won't show you many results, but what was interesting is that with this simple approach, we for a specific data set, we were able to get performance that are comparable to a recurrent neural network. But the difference is that in our case, we didn't really use temporal information, while recurrent neural networks, they really try to associate different frame and learn some kind of temporal associations. While in our case, the only thing that we were doing is giving an importance to each frame, and that seems that for this kind of data was enough to obtain very good performance. The second part of this work, it goes really into the sampling, because so far we didn't show any sampling. We just proposed this softmax pooling for learning the emotion in a video. But the second part is about how to scale up this approach. If we want to go to even better performance, we need to move from 2D CNN that analyzes one frame. I see that there is a question from.
Marco, I know next to nothing about what you're talking about, but how related is this to video compression? From what I understood is that in video compression, you focus only on the parts of the video that actually change from one frame to the other, so you minimize what data is actually transferred. So it in some ways sounds to me like it's orthogonal.
Yeah, in the sense here we focus on the part that is more discriminative for the task. In this case, for recognizing emotions. But I don't know much about video compression. But as you said, there the most important part is to focusing where there are changes. So in this sense, yeah, probably they are orthogonal. I'm just trying to think if some kind of importance, learning importance of the frame could be applied also there. Not fully sure, but maybe there can be some way.
And when you look at the frame, you look at the whole picture, right? You don't filter, you don't say, I focus on the shape of the face.
Actually, I skip many details, but so what we do is a kind of pre-processing, because you have a large image where the face of the person is a small portion of the image, but we have a first step that is cropping the face, finding with the detector the face and cropping it so that we analyze only the face.
Okay.
Okay, thank you for the question. Okay, I will go on with this, and I will try probably to go a bit quicker with the other applications, because I don't want to take too much time. But then if you have any questions, please feel free to ask, and I could give you more details. So the second part of this work about emotion recognition in videos, it's about using 3D CNN. So in 3D CNN, we consider the two spatial dimensions as in a 2D CNN, but also the temporal dimensions. So instead of analyzing one frame at a time, we analyze a short clip of our long video at a time. The best will be to analyze the entire video with a 3D CNN, but it's not feasible because of memory issues. The entire sequence wouldn't fit into memory. So what people have been doing, it's sampling small parts of these videos, short clip of the video, and analyzing those with 3D CNN. But still, even with this approach, 3D CNN are very expensive. They require a lot of parameters, memory, and computation. And also, we lack on emotion recognition, we lack of large data sets. So the previous approaches, as I already mentioned, what they were doing is sampling uniformly to, instead of analyzing the entire video in one shot, they sample a small part of the video, and every iteration of the training process, they sample a different part of the video randomly. In this way, again, because of Monte Carlo sampling, what they're getting, it's an estimation of the entire video, which will lead optimizing still the same loss as if we consider the entire video, but with an increased variance. But this makes this approach feasible, because otherwise we won't have enough memory to really do that. And then there are other details that I will probably skip to be able to use 3D CNN with the small data set, like using the weights of 2D CNN, what we call inflate 2D CNN to pre-train a 3D CNN. But this was like previous approaches. What we propose is to apply our softmax temporal pooling on these 3D CNN models. And for doing this, again, we will need to sample. But instead of sampling uniformly, we will sample in a way that we will be able to perform softmax temporal pooling. Here, I show the three different ways that we could sample in a video. The first way, it's what I already mentioned, uniform sampling. So it's, again, a kind of Monte Carlo, where the sampling it's uniform, and with a few samples we can still estimate the global average pooling of a video. The second one is softmax temporal pooling, where we add this W on our function so that we assign a weight to each part of the video to give more importance to the parts that are more discriminative. And the third one is, again, the softmax temporal pooling with importance sampling. And I will show you more in detail what is with these illustrations. So the first one, imagine that we have a function f that is representing the score of a certain action. And over the x-axis, we have time. And then we want to use pooling. The simplest thing and the thing that was done in previous work was to use average pooling. So we give the same importance to each frame. And then we are also sampling, and we sample with a uniform distribution. So also the sampling is uniform. So this is what is done in previous approaches. And the good point is that we can, with this, we still reduce memory and computation, because instead of considering the entire video, we just sample small parts of the video at each iteration of the learning. And also we have the same objective in expectation, because as I said, when we use Monte Carlo sampling, we get an estimation that is unbiased. But the drawbacks is that we are still considering giving the same importance to each part of the video. And we saw that if we are able to assign more importance to the discriminative part of the video, we can improve the performance of the method. And also we have an increased variance due to the fact that we sample. Second approach is, if you see, it's almost the same thing, but instead of pooling uniformly, we pool with something proportional to our function itself. And this, as we said, it's correspond to add a WT, a weight, to each short clip of our representation. And what we can use this softmax temporal pooling with Monte Carlo sampling by sampling uniformly. And this will give the advantages of Monte Carlo sampling, so reducing the memory. But it will increase, and also we will have the advantage of softmax pooling to focus on the part of the video that is more important, but will increase the variance of the estimation because we sample uniformly. So we will have parts of the video that are more important, but we sample uniformly. So a big part of the time we sample part of the video that are not so interesting. So what we did is to, instead of using the weight associated to each short clip of the video, to use it directly in the softmax pooling estimation, we move it to the sampling. What does it mean? Instead of sampling uniformly, we sample proportional to this weight. So instead, you see here in the image, we have a pooling that is proportional to our scoring function, but we have a sampling that is uniform. And now what we will do is exactly the opposite. We have a pooling that is uniform. So you can see in the formulation here, the approximation of the formulation on the right. We don't have anymore the weight WT associated to each short clip, but we, instead of sample uniformly, we sample with a function that is, again, proportional to our scoring function. So what does it mean in practice is exactly using importance sampling. Instead of sampling uniformly, we can sample more where we think the part of the video in which the expression, in this case, the motion, it's more likely to be there. So with this approach, we have the advantages of, again, Monte Carlo sampling, because we sample at each iteration of the training only a small part of the video, but we have also the advantage of softmax pooling, and we reduce the variance of the estimation, because instead of sampling uniformly, we sample with a multinomial distribution, which is proportional to the weights. So far, everything is fine and nice, but the only drawback is that as we use W, the weights to sample, we cannot use backpropagation to learn these Ws. So we need to find another way to learn the importance of each short clip of the video. So how to estimate this W? I wouldn't go in very much into detail, but the idea is that we have an additional variable Q that is associated to each frame S or each short clip S of the video. And this Q, it will be equal to the scoring function F that tells us how likely is a certain emotion to be. And at each iteration, we use Q and we renormalize Q with the softmax. And we use this renormalized Q as weights W that we use to sample. So as Q, it's equal to F when we sample, it means that WT will be very similar to the previous WT that was directly the softmax of the scoring function. So it means that in this way, QS is an approximation of the previous softmax pooling. So it means that we are sampling with an importance that is proportional to the softmax weight. So we are approximating the softmax pooling. And this works quite well. Here we can see an example. We have a sequence on the bottom left, a sequence of a video where the actor is expressing some emotion. And on the right, we tried the same also for actions. In this case, we have a person in a video performing a cartwheel. And what we see at the top is the estimation of the importance of the emotion over frames with uniform sampling. And lower, we see the same estimation with weighted sampling. And we can see the estimation is not exactly the same, but it's quite similar. But the difference is that with uniform sampling, we need many more samples to be able to get a good estimation of this, of the importance of each frame. While with our sampling that focuses on the most likely part of the video to contain the emotion or the action, we can see that the sampling, which is represented here with the dots, the blue dots, sampling is performed mostly in the part of the video that is containing the action. So that's why we are able to obtain similar performance, but save quite some computation. And here we show results on a data set of emotion recognition. And at the top, there are some previous approaches. I wouldn't enter into detail, but again, there are some approaches based on recurrent neural networks or other kind of weighting. But what we did is take a simple baseline, actually two baseline. One is based on C3D, which is a simple 3D neural network. And another one is based on an inflated version of VGG for 3D convolutional recognition. And we see that in both cases, we start with uniform sampling that gives a certain accuracy. And when we introduce our softmax pooling with sampling, we are able to improve the performance while having similar computational cost. So you can see again it's a trade-off between computational cost and performance. In this case, we have similar computational costs, but increased performance. And with this, I finish the first application. I see that it's already more than half an hour that I'm talking. I don't know how much time do I have to go on with the other, just to have an idea of how quickly to explain the rest.
Yeah, about 15 minutes, but
Okay.
I have a question. So
Yes.
since we are changing subject.
Sure.
Again, this is not exactly related to machine learning, but there is a science of expressions. For example, if you want to do drawings, so some of the drawing manuals, they go into the anatomy of facial expressions. And so they tell you that an expression is the result of different contractions of different muscles. I don't remember their names.
Like action units.
I'm sorry?
Action units, sometimes they call it.
Yeah, so if you have this muscle and you pull this much, then you make it like this. And then if you have this muscle, and so it's almost an algebra of expressions based on the contraction and the pulling of different facial muscles. And I remember in the book that I read, they were talking about some experiments that a French scientist did in the, I don't know, like the turn of the century, with actually electric shock. So he was able to get somebody to smile, even though they were suffering actually from the electric shock, because he just prodded the right muscle, and they had this. It was a very weird expression. So,
yes.
So my question is for facial expression in general. Like I'm thinking that because the interestingness coefficient, the W that you mentioned, that weighs the different frames. So you did like a posteriori estimation of what the W is. Is there a way to estimate that interestingness of the frame, for example, based on a specific recognition of, for example, relative positions between, I don't know, specific points in the face with the eyes, or like do some segmentation and then compare the relative positions of the different parts of the face?
Yeah, it's...
Has there been any work done along those areas?
Yes, there are quite some work in that. So also in our first work, I didn't mention that because it was a bit going in another direction, but apart from the temporal pooling, we had also a spatial pooling where instead of considering again every part of the frame with the same importance, we associate an importance based on the discriminativeness of each part of the face. So in this sense, normally the model was focusing mostly on the eyes and on the mouth, because were the parts that were more discriminative. So this is an approach based on attention. So at every frame, we try to find which parts are more important to focus on in the face. But there are many works on that, and some are based on these action units where they know already which part of the face should move for a certain emotion, and then they can use that as additional information to know already where to search for the emotion. But it adds a bit of complexity because we need to introduce these action units and to pre-code all the different action units. So there are the two ways. One is with this knowledge a priori, and the other way is trying to to get this knowledge from the data, but of course you need a lot of data and it can be noisy. Perfect, thank you.
Can I just ask a
Yes.
quick question,
Sure.
which is again like Hafid, I'm really very far of what you're doing.
I hope I give
no, it's really
understandable,
and yeah,
okay.
it's for me it was great. It's just can the techniques you are using detect deception, or someone who's having some expression but it's for deceiving? So I was wondering if this kind of emotion, well, I don't know, expression which is meant to deceive can be also detected. It's really a naive question, and
no,
far from
now I don't remember. I think in our the data sets that we use for these papers, we had 6 or 7 main emotions like happiness, angry, neutral emotion. But I'm not sure if there is something similar to being deceived. But in general, I mean, of course, there are emotions that are easier to detect and others that are more difficult. But now we're starting a project also with Simon Bacon and Eric Granger, where we are trying to detect ambivalence, which is also a very difficult expression because it's very subtle and it's something quite new, but we are trying to do that. Not sure what will be the result, but it's interesting.
Okay, thank you.
Welcome.
Do we still have time for questions?
Sure.
Okay, so me also, I don't have a deep background in deep learning and in data science in general, but I have a background in information theory and in coding. So my question is, when you do the sampling, do you have any theoretical measure to know if you lose information? And in I know you reduce data, which is the objective, but do you reduce the entropy of the information or the information itself according to the information theory definition of information?
Yeah, I'm not sure in terms of information if we lose, but I will give you a very naive answer in the sense I don't have the theoretical results about this. But the good point of using this sampling approach is that during training, we analyze the same data multiple times. And every time we perform a different sample, we extract different samples. So over time, we will end up again to see most of the data. It's just that instead of seeing it, all the data at every iteration of the algorithm, we see only a part of it.
Okay, so my understanding is you are using some smart manner to reduce the data without reducing the information included in the data.
Yes.
Okay.
Yes.
Okay, which is good. Yeah, very good. Thank you.
Thank you. Okay, if there aren't more questions, I go on with the other parts. This is a joint work with people from Ericsson with a MyTalks project with Zhongwen, Francisco, and Nishank at Ericsson, and my Eric Granger, again, my colleague at ETS, and our student Akil. And the idea of this, it's again an application of the same concept, but in a slightly different context. And the idea is that we want to perform object detection. So we have an image, as here you see a cat, and we want to find a bounding box that localizes the cat in the image. But the difficulty is that during training, we don't know where the cat is. We know only that in the image there is a cat. So it's what if we add the bounding box of the cat, we will call this fully supervised object detection during training. But if during training we know only that there is a cat, there is an object or multiple objects in an image, but we don't know where they are, then this is called weakly supervised object detection, because the annotations, the labels that we have during training are weak. They don't tell us exactly the answer to our task, because our task during once the model is trained is to really localize the object with a bounding box. So here it's exactly the same. Fully supervised is where we have the bounding boxes during training. Weakly supervised, we have only weak labels that tell us what is in the object, but not where it is. So for full supervision, what people normally do is to compute probability of a certain class of object C given an image X, and this probability is computed again using a softmax over classes. So imagine that we have 10 classes of different objects, and for each class we got a score that tell us kind of how likely is to have an object in the given bounding box. And so what we do is normalizing this score so that they become probabilities, and the class that has the highest probability is the winning. So we associate that bounding box to that class. But again, in our problem, we make things more complicated. We don't have the bounding box during training. So we still need to find a way to train our model. And what is done is to compute again, instead of computing the score of or the probability of a class given a bounding box. Here we compute a weighted sum of the scores of all bounding boxes in an image, so that we will learn during training which bounding boxes are more important and which bounding boxes are more likely to contain the object of interest. And here you can see that it's again the same thing. We have a set of possible locations, in this case, a set of possible bounding boxes, and we want to find which one is the good one, which one contains the object. So again, it's a kind of max operation. We want to find the bounding box that scores the highest. So again, we can use the same approximation as before. Instead of computing the entire weighted sum of all the scores of bounding boxes in an image, we can approximate them with by sampling. And again, we can sample, we could sample uniformly, but it's even better if we sample based on the importance of each bounding box. So in practice, it's the same approach as before, but here instead of localizing something temporally, we localize something spatially. So each bounding box will have a weight, and we will sample from the bounding boxes that have the highest weight. But then there are some small problems. First of all, if we use all possible bounding boxes, it's unfeasible, because if we have an image with n pixels, we will have n square number of bounding boxes, because a bounding box is defined by 2 pixels, the bottom, for instance, the top left and the bottom left pixel. And so it means that, for instance, an image of 100 by 100 will have 10,000 pixels and 10,000 square bounding boxes. So it's unfeasible to evaluate all these boxes. But what we normally do and what people do in this case is to use proposals. So we have some segmentation methods that will tell us already which are the bounding boxes that are more likely to contain the objects. So we can already reduce the computational cost, and we use these proposals as locations where we associate a probability to sample. So with this in mind, we have already our method. The last part is that there is a mismatch between the proposals that are given with our segmentation algorithm and the detections, because we have an algorithm that can detect objects, and the detection may not match completely with the proposal. Here, the proposal is in red and the detection is in green. And you can see there is some overlap, but it's not exactly the same location. So for this, the update of the weights, instead of being exactly as the formulation before, we modify a bit this formulation such that it takes into account the fact the overlap of the detection. The detection gives us a score, and the proposal has a certain overlap with the detection. If the overlap is 100%, the score given by the detection will be associated to the proposal. If the overlap is less, there will be also weighting to the amount of score that is given to the proposal. So to see the entire process, we can see it here. And the nice part of this work is that in this specific case, we don't care about the detector that we use, because our approach can be used with any detector. So you can see in the middle, we have a kind of any detector that can be used. We need something that, given a ground truth, will produce a detection, because once we have this detection, we can use the score of this detection, and with our weighting rule that compare the detection with the proposals and assign a score proportionally to the overlap between the detection and a proposal. And once we have the weights for the proposals, we can sample from these proposals, and the sample proposal is given to the detector as a ground truth. It's of course, it's a fake ground truth, but if we train with this approach, over time, the proposals that are more likely to contain the object will have highest probability to be sampled. So at the end of the training, if everything went well, we will have samples that will mostly focus on the object of interest. So we will end up training with good ground truth that are learned during training. So this approach was already evaluated on some standard data set on, I didn't mention here, but it's VOC 2007, which is a standard data set for object detection. And we can see that if we evaluate it in terms of average precision, and we can see that if we have full supervision, we obtain almost 70%. So it's quite good. If we use weak supervision, we can obtain something, but much lower in terms of average precision. And it's expected, because we don't provide bounding boxes, and there can be very noisy cases where there are multiple objects, some very small. So it's very difficult for the approach to really find them. But if we combine this weak supervision with also another kind of approach that can also try to focus on the object of interest, I wouldn't go in detail, but we go to 35. And again, if we use these weak annotations plus 10% of bounding boxes of fully annotated data, then we reach 60%. So we get very close to full supervision using only 10% of labels. So that's a promising result. We still need to analyze a bit more our results, and then we will probably try to publish this work. And I will go very quickly to the last direction of research, the last project. This project was done is done with Ismael, also a colleague at ETS, Cypra, which is our student at ETS, and then two researchers at LMNTI, Pau and David. And the idea here, it's still very similar to the previous one. So it's still weakly supervised, but this time instead of object detection is object localization. It's this terminology, it's very specific of this research field, but in our field, we call detection when we want to detect, to localize with bounding boxes multiple objects in an image, and we call localization where we have only one object in the image, and again, we want to put a bounding box. So it's a slightly easier task because we assume that we have only one object in the image, but it's still very interesting. And for this one, normally what people do in research is to use class activation maps. So we divide the image into small parts, and for each part, again, we associate, we learn a kind of score, and then we can select the part where the scores are higher, and this part will be the bounding box of the object, and we will need some thresholding. But this approach is not performing very well, and has also some other drawbacks. But what instead we want to do is to associate a distribution to the location of the object. And we use, for the moment, we use a Gaussian distribution, but we could try also with more complex distribution. So we have a Gaussian that represents the X and Y location of the object, and also the scale of the object that can tell us if the object is small or big in the image. And as we talk, we use distribution, we use a Bayesian approach where we try to learn the location of the object in a Bayesian context. So in practice, what we want to achieve is we have at the beginning of the training, we have the initialization of the location of the object, and we will initialize with the Gaussian center in the middle of the image and with large variance. But then during training, we get more information about the location of the object. So mu, which is the mean of the X, Y, and scale of the object, will move to the right location. And then with further training, we hope also to reduce the variance of the location, because we learn more about the appearance of the object, so we can learn where is exactly the object in the image. Very quickly, I will present the Bayesian formulation, but I wouldn't go too much in detail, but feel free to ask questions. So the idea is that we want to estimate the object location, P of L, the probability of the object location, given the Y, which is the object class. And for doing this, as I said, as you can see here at the bottom, we have the observable variable is Y, the object class, and the location is what we want to estimate. And for doing that, we use a Bayesian approach where we have we sample the likelihood of a certain class given a certain location. We multiply this by a prior of the probability of each location in an image, and we divide by the total probability of a given class. And here the problem is that the total probability at the bottom it's difficult to compute. We will have to sum all over possible location, and even if we use proposals, that will get computationally very expensive. So instead of doing this, we use a variational approach where we assume that the prior of the location, it's Gaussian, and also the posterior that we want to estimate. So the location of the object given the score, the probability of a given class. And we assume that to be also approximated with a Gaussian. When we do that, we, again, I won't go into detail, but we can, after few changes in the way to represent our loss, we can see that our loss can be expressed as a first term that is the log of the probability of y, the class. So this is cross entropy. So this is standard. Oh, I see a question.
Yes, if you can go back to the previous slide.
Yes.
So when I look at this, just the first formula,
Yes.
which is the only thing I understood. So if you take pictures where you know there is an object, isn't P of y equals 1? If the pictures that you choose, you know that each one of them contains a cat.
Yeah. Sorry. What I didn't mention is that we have multiple classes.
Ah, okay.
So it's a probability over all these classes.
Okay.
P of y is probability in all those classes, you say?
So P of y, it's we can have 10 classes, and so we have 10 possible values that are normalized to sum up to 1.
Oh. And later on, just to understand your notation, you say priors P of L given X is in, for instance, mu PR, comma, sigma PR. That nu is the distribution. What is that? The capital N.
Sorry?
In the formula where it says prior, P of L
Yeah.
given X is equal to squiggly N of mu PR.
It's a normal distribution.
Ah, okay. With the mean.
With parameters mu and sigma.
And mu and sigma are functions of P and R.
Mu and sigma are given in this prior. So we define a priori what will be the.
Yeah. Okay. Yeah.
And what we want to estimate here, it's the mu and sigma of the posterior.
Yes. Right.
Okay.
Thank you.
Welcome. So finally, we will have a loss that is cross entropy. So maybe also something that here it's a bit misleading. I didn't, in all this formulation, when I say P of y, it's actually P of y given x, where x is an image. So I avoided to say every time that I give an image, but it's there.
Yeah.
So this part is standard cross entropy for classification. And the second part is the KL divergence between two distributions. One is Q, which is our posterior that is approximated with the Gaussian, and the P of L given Y, that is the real posterior. So we want that our approximated posterior Q to be as similar as possible to the real posterior. So this is our objective. to be able to first properly classify the right class in a given an image, and second, to have our posterior, that our approximation of the posterior, which is Gaussian, to be as similar as possible to the real posterior, that can be anything. But instead of really computing this, what we do, it's equivalent, and we could show with some passages that it's equivalent. And what we can do is optimizing the expectation, sampling the location of the object with our Q, that is the approximated posterior, of sampling, so the expectation of the logarithm of our likelihood, plus a second term, that is the KL divergence, this time between our posterior, approximated posterior Q, and the prior PL, which we said we defined to be Gaussian and predefined. In practice, what does it mean? This we have a model where we have for each image, what we want to do is to sample from a Gaussian distribution, and this Gaussian is transformed with some parameters that we want to learn, that will tell us where to sample, so will tell us the location of the object. We sample a bounding box in the image. This bounding box will be cropped and passed to a convolutional neural network with parameters W. This convolutional neural network will give us the likelihood, so the probability of a given class given the location. And with that, we can compute our loss, that is the expectation sampling from the Gaussian distribution of the likelihood. So this term, it's computed in this way. Of course, we can sample multiple samples to get a better estimation of the expectation. And then we'll have a second term, that is the regularization, that will tell us that the estimated location of the object to be similar to the prior that is predefined in Gaussian. So to be more detailed, and then I'm finished, we'll have three phases for this approach. We have first sampling the location from Q. Then second phase, crop the image with the given, sorry, here it's not Q, but it's the sample that we obtain, call it L. And third, we obtain P of Y given L. And with this, we can compute our cross entropy loss. And this loss is used to update W and theta. So in practice, we can think about this as a kind of expectation maximization, but on distribution instead of on points. And with this approach, we update the object position, and we estimate the appearance of the object and vice versa. And in this way, we can learn both things. And this corresponds to learn W, the appearance of the object, and theta, which are the parameters of the location of our Q that represent the location of the object. With this, I'm finished. So to summarize, what I wanted to present and to tell you today was that Monte Carlo sampling and also variational Bayesian optimization are powerful tools to reduce computation during training. In practice, with sampling, we can reduce the memory footprint and computational cost of training deep learning models. And there is still a lot to do. For instance, we need to estimate the quality of the obtained solution. So for instance, how many samples we need to sample to be able to obtain good results, because there is always this trade-off between number of samples and variance in the estimation. And then there are many other points that can be discussed, like discrete versus continuous distribution for the estimation of these variables. And Monte Carlo sampling can be probably used also in other parts of the learning, and also using more complex distributions like mixture of Gaussians or other things can be also an interesting way to improve results. And with this, I'm finished with the talk, and I'm open to any question.
Merci beaucoup. C'était fascinant. Excellent presentation. So when we say that I don't know anything about this, that's actually a positive for us, because we always like to bring people to talk about things we don't know about. So that's an advantage. That's not a disadvantage.
Yeah, I hope I was clear enough. And
yes, absolutely.
Sometimes there are many details that I missed or I didn't explain in detail, but
yeah, you should worry if nobody asks any questions. That usually means they didn't understand anything. So
well, I didn't understand it, but I do have a question. You talked about, can you describe in 25 words or less this concept of, what do you call it, cross entropy? Next last slide, I believe.
Yes. Like here or here. Yeah.
Yes, you call that crossover entropy.
Cross entropy. Yeah.
Yes. Can you describe that intuitively? I don't have any feeling really what that means.
So it's what it's normally used in for learning a model when we perform, for instance, object classification, and it's minus log of the probability of a given class. So that means that if the probability of the expected class is low, we get the log of something close to 0, which we obtain a loss that will be very high. Yes. That means that we try to push to 1 the probability of the correct class.
Okay. That'll set me on my path. Thank you.
Welcome.
Est-ce qu'il y a d'autres questions? Bon, je pense là, on a quand même posé des questions pendant la présentation. Donc, d'autres questions? Going once. Going twice. On va faire comme les enchères. Alex, tu n'as pas de questions? J'avais vu Robert Godin, il s'est inscrit, mais il a dû avoir un empêchement. Ça aurait été bien de le revoir. Robert Godin est un professeur qui est à la retraite depuis 5 ou 6 ans. Donc, il s'était inscrit au séminaire, Marco.
OK.
Mais
peut-être j'ai une, je ne sais pas si c'est une question ou un commentaire, mais est-ce que j'ai l'impression que tu as essayé de résumer le travail, mais ma question, est-ce qu'il y a un travail théorique derrière pour revenir à la cross-entropie qui a été définie? Bon, in information theory, cross-entropy, it means how many relations there is between the two informations. So we use this in communication systems to know how many information there is between the received signal and the transmitted signal.
Yeah, in this case, you can think about the two signals as ground truth. So
yes, exactly. It's the input and the output of your before and after sampling.
Yeah.
So do you have any theoretical information to know if you lose information? But because what could be more interesting than only reducing the data is reducing the information and still having good results.
Yeah, when we do learning, it's you have imagine for image classification. We start with an image which contains a lot of information, and we end up with a class label, cat or dog.
Mm-hmm.
So we are in the process of doing this. We are reducing a lot of information, but we are keeping the information that we need, that we want. So in this sense, we are reducing the information, and there is some theoretical work that shows how the information is reduced through layers of deep learning model. And then there are also works that are using like mutual information for trying to learn, for instance, clustering or some unsupervised approaches.
Yeah, very, very nice approach. Yeah, thank you.
You're welcome. And yeah, feel free if you think that something similar can be used in your field of research. I will be happy to maybe collaborate or try to have some
Of course.
brainstorming.
Yeah, actually, I don't use this anymore, but I used to be familiar with speech coding and video coding, which is to reduce the amount of information before transmitting this to the minimum, but without losing information. So this looks somehow similar, but it was the first question by Hafid. Like, because it looks similar to video coding when you do sampling. Yeah. Yes, of course. Thank you.
Welcome.
D'autres questions? J'ai peut-être une question philosophique. How much you can just speculate about it. I mean, I don't expect an answer, just some reflection, just some speculation. But like here in the approach that you showed, and I would say this is fairly common in machine learning work, which attests to the strength of machine learning. You make almost no assumptions about the domain, and you still manage to get some very good results. So si je le caricature, c'est une caricature. I remember a friend of mine once sent me something. He said, "Can you believe that somebody actually trained a neural network to play chess just by analyzing pixelized images of chess configurations?" And so I started my academic career doing symbolic AI, and that always comes back. That always taints all of my questions. But to what extent, like if we did some modeling, some a priori modeling of the problem, how much computation can we save? So I asked the question, for example, about the muscle movements and etc. So if I knew that the expressions, you said action units, and you said that there is some work in it, but like how much savings do you think we can accomplish in terms of computation if we did preliminary modeling? And I don't know to what extent, but anyway, so.
Yeah, it's again a kind of trade-off in the sense that you want to spend more time on modeling the problem or on collecting data. It's if you have a lot of data, you can manage to estimate many of these variables like action units and other things. But on the other side, if you have a limited amount of data, then you really need stronger priors, and there a model of the specific problem can be helpful for sure. So it's finding the right balance.
Yeah.
And yeah, the machine learning community is going towards reducing as much as possible prior information, but this comes to the cost of a very large amount of data. But
And
the
money.
assumption is that computation is always increasing, so we are able to compute more and more data in fewer time, and so we can reach good performance with weaker priors. But for sure, it's always a question that we have to ask ourselves. Given a problem, given a certain amount of data, which is the best solution? What part? Maybe we can model something very simple, but we can already add some good priors to lead much better results.
Excellent. Donc, s'il n'y a pas d'autres questions, on va vous remercier encore une fois pour une excellente et très intéressante présentation.
Yes.
Merci beaucoup.
Merci beaucoup, Marco.
Merci beaucoup.
Thank you very much.
Thank
I enjoyed
you.
it immensely. Hope you'll learn more about your work in the future. Wish you best of luck.
Thank you.